Good morning, everyone. Thank you all for being here today. Today, we're very lucky to have Ryan Chornock giving the colloquium. Ryan did his PhD at Berkeley under the supervision of Alex Filipenko before moving to Harvard for a 5-year postdoc working for Ido Berger, and then moving on to faculty jobs at Ohio, Northwestern, and now back where it all began in Berkeley. Ryan has worked very broadly across transient astrophysical phenomena, supernova and gamma ray bursts, and now leads the tidal disruption event ZTF working group. Tidal disruption events are a very exciting frontier in time domain astronomy, and I'm sure we're about to learn a lot about looking for black holes in all the wrong places.
Okay. Thank you, Andy, for the kind introduction, and of course, for giving me the opportunity to present in front of several people in the audience who have been trying to model the things theoretically that we are finding observationally. And the theme of my talk is sort of trying to see how we can expand our search for these tidal disruption events and what that allows us to actually learn that is new. And so this is the artist rendition from the press release of one of the objects that we'll spend a lot of time talking about later on. But before we get started, I wanted to say I've been working on tidal disruption events for quite a while now, 15 plus years. But I only recently joined ZTF and I'm chairing the TDE Science Working Group about 2 years ago. So when I talk about the older results from ZTF, that's other people. I'm not taking credit for that. And when I'm talking about the new results, I will give a shout out to all the wonderful postdocs who are actually leading all the analysis and research. All right. So the idea here is that tidal disruption events are cool, but they also are useful. So the basic background is, of course, that we know that there are many supermassive black holes in every massive galaxy. We can dynamically measure their masses out to some distance of maybe 30 megaparsecs or so. If they're not actively accreting, though, we have, it's hard to find them and detect their presence without the presence of active ongoing accretion, like in an AGN. And so how can we learn about the populations of black holes that we can actually see? And this is where the tidal disruption events come in. So the basic idea, and look at the little zoom in box up there. There's a tiny little spot. That's the black hole. And this is a random star in the nuclear vicinity of the galaxy. It experienced some sort of dynamical encounter, perhaps 2-body relaxation, which sent it on an orbit that caused it to pass close to the supermassive black hole. And as it does so, it gets tidally stretched out if it comes within the tidal radius. And the tidal radius is where the tidal gravity in the supermassive black hole's gravitational field exceeds the self-binding energy of the star. And so when that happens, the star gets stretched out, it gets destroyed, and the gas cloud then goes away. So let's run through this a few times. You're going to see a zoom in over here. Star is tidally disrupted. It's stretched out into spaghetti. About half the star is gravitationally bound to the black hole. About half the star is unbound and flies off. The half that is bound comes back, and then through magic, it forms a disk. And this is one of the big theoretical uncertainties, is how exactly do we convert this debris stream into actually something like a disk that you can write equations about. And so for typical parameters here, we're talking about disruption occurring at tens of gravitational radii around the black hole for a solar type star. So this is an old idea, it was discussed by Hills in the 70s. Martin Rees had a famous Nature paper back in 1988, which sort of set some of the naive expectations for what we should see if these events were to happen in a galaxy. And the idea is that you have an immediate disruption. And of course, this is a cartoon, so there's no numbers on the units. But you have immediate disruption, then nothing happens. Nothing happens because the debris stream is still flying away from the black hole. You have to wait some fallback time scale for the most tightly bound material to return to pericenter, and then something happens. When the accretion turns on, you get a sharp rise, and you get a decay. And back then, Martin Rees pointed out that there should be a characteristic power law behavior of the decline of the emission from the TDE, which is based on Kepler's laws, that you have a roughly constant spread of specific energy. And so just by applying Kepler's laws, you get a T to minus 5/3 power law for the return of mass to pericenter. And a couple other important points here. One is that massive black holes above 10^8, a few times 10^8, depending on the black hole spin, the tidal radius is inside the event horizon, so they cannot produce TDEs. So our typical fiducial here is something like a 1 solar mass star around a 10⁶ solar mass black hole. And for those parameters, the naive expectation is that the peak mass fallback rate is super Eddington. So we'll experience a period of super Eddington accretion, but which will drop as a power law. And as it drops as a power law, it will go through the different accretion regimes relative to the Eddington rate. Okay? And so this gives us a new window into learning about black holes. So we're learning about black hole accretion under different conditions than we see in either steadily accreting AGN or galactic X-ray binaries that undergo repeated outbursts to different mechanisms than what we have here. But one of the things that we're going to talk about today are how we can use these to find black holes. Because all you need is a black hole encountering a star. Well, it's kind of hard to get the star there. There's a lot of information about stellar dynamical processes in the vicinity of black holes that there's probably people in the audience who know a lot more than I do about that. But for today, we're going to focus on the idea of using them as a signpost. And lastly, I wanted to use that also as kind of a case study for how we go about looking for rare new phenomena in large optical transient surveys. Because the thing that's hanging over all of us is that Rubin and LSST are turning on soon. And there's a lot of promise for extracting new types of astrophysical phenomena. Here's an example of a phenomena that we know exists. We have found them, and yet it's hard. And so there's a number of lessons to be learned from that. So over the past, let's say 15 years, as optical transient surveys have matured, we start finding these TDEs at a rate of roughly once a month. And this is a compilation from my postdoc Erica Hammerstein of early ZTF TDEs. And these on the middle here is a plot of sort of the bolometric, really just the UV optical component, light curves for a bunch of TDEs. And so what she's done is taken the multiband photometry, fit a single temperature black body, again, big assumption embedded there, and plotted luminosity of black body versus time, and on the right, the temperature of that single temperature black body over time. So for typical sort of parameters, we get kind of a rise time scale of a month. We get a peak luminosity around 10 to the 44 ergs per second in the UV optical component with quite a significant spread, so maybe an order of magnitude on either side of that. But two key points come out of the basic analysis of the observed optical features. One is that if we look at the temperature as a function of time, it's kind of flat. And this is log T, so these turn into things like black body temperatures of 20, 30,000 Kelvin and relatively constant. That's going to be critical for the way in which we actually find tidal disruption events, as it distinguishes them from many other classes of astronomical transients. Supernovae explode, they cool via adiabatic expansion, and their temperatures drop over time. Accreting black holes sort of remain roughly constant. But the tricky part is embedded in this last number here. So I told you that the typical parameters for a typical tidal disruption event are that the star will be disrupted at tens of gravitational radii, which for a 10 to the 6 solar mass black hole is a few times 10 to the 11 centimeters. So the black body radii that we infer are between 10 to the 14, 10 to 15 centimeters. So we have an optically thick photosphere beyond 1,000 gravitational radii for an event that occurs at 10 gravitational radii. Stuff has to get from point A to point B and remain optically thick. And this has proven to be a big theoretical challenge in interpreting what are we actually seeing. We don't know what we are actually seeing is the short answer.
These are optically defined or?
Yes, optically selected. Yes, yes. So yes. Yeah, we are setting those aside for now because I want to tie everything to selection through optical surveys. But you're correct. As a sample, for example, the eROSITA SRG has found a population of TDEs that are found in the X-rays, and most of them have no associated optical flare. A few do. And so if you try and convert this into an event rate, it kind of doubles the apparent event rate. If everything that they're claiming is a TDE is a TDE, and if the intersection of the Venn diagram is a little hard to figure out, but there's going to be a lot of twiddle numbers here because of this sort of issue. Yeah, and a related point is that you might worry about extinction for something that's extremely bright and occurs in a galactic nucleus. The MIT group has found a population of infrared flares that they have claimed are tidal disruption events. I'm not as confident that everything in their sample is a highly extinguished tidal disruption event, but it does add to the picture that there might be events we're missing, for sure. Yeah. Yeah, so stepping back to this question, I wanted to walk you through sort of the chain of evidence where we go from the thing that we can actually robustly theoretically calculate, which is what happens to a star when it passes in the gravitational field of a black hole. It gets torn apart. You can measure, you can run a simulation. You can look at the distribution of the orbital energies of all the little packets of gas in that star. And at the other end here, we have some sort of light curve at some sort of frequency as a function of time. Each step in this chain involves making some assumption to proceed. Okay, so going from the orbital characteristics of the disrupted star, this turns into some mass fallback rate to pericenter based on Kepler's laws. And good thing Kepler's laws we believe in. But then what happens? If you have a bunch of gas coming in to 10, 30 gravitational radii, it's not actually reaching the black hole at that point. So one of the big controversies is whether or when a disk forms and whether the material that we see is actually accreting onto a black hole at that time. It's often frequently either explicitly or implicitly assumed that this mass fallback rate at pericenter is actually the accretion rate onto the black hole. This may not be true. But even given that, you have some accretion onto a black hole, which produces some luminosity through some prescription. But what we just said was that the optical blackbody radii that we see are way too large to be a disk forming at the tidal radius. So there has to be some other process that is generating material that's outflowing to large radius and is reprocessing whatever is generating the optical light. Okay? So a larger fraction of the emission comes out in the optical than you naively expect. If you're just to write down a bare thin disk model with the appropriate m dot and the appropriate mass of the black hole, you'd expect a lot of X-rays that we don't necessarily see at early times. And so a lot of our uncertainties in understanding what we're seeing come back to this issue. Yeah. So there's two very different pictures in the literature, two very different classes of models that people talk about. One is that there is a disk down below. This is from Jane Dye, where you have some debris stream that forms a disk that's actually accreting. There's outflows off the surface of that disk that are thick, and those outflows are preventing you from seeing directly down to the surface of the disk unless you happen to be looking directly down the funnel, and you get different ratios and proportions of X-rays and opticals depending on your line of sight. A second class of models uses the self-intersection of the debris streams to produce shocks where the debris stream interacts. And those shocks can then produce X-rays, which are then surrounded by a bunch of junk from the disruption, and we'll reprocess that into the optical if they're optically thick. But to some extent, it doesn't matter for our purposes, but it is hiding underneath whatever the photosphere is doing. And there's another issue, which is actually, why are these things so faint? We find them at 10 to 44 ergs per second, and that's really kind of bright. But this is an old plot from a very old paper of mine that pointed out something that has since been seen in different ways and is now called sometimes the missing energy problem of TDEs. That stellar mass is 10 to 54 ergs. That accretes at 10% radiative efficiency. Then you should see 10 to 53 ergs come out as light. And in our best case scenario, we see 10 to 51 ergs in this UV optical component. What's going on? And if you just take a mass fallback curve from one of these models, you apply some very simple assumptions, you can get curves that go up and down through the optical light curves that we have, but with a scaling that implies the total amount of mass involved is of order 10⁻³ solar masses, in order to avoid the energy problem. So there's various arguments about whether this is a real problem or we're missing stuff, but it may mean that many of the things we claim are tidal disruptions are actually partial disruptions. That was what I put forward back then, but it's a really big issue that we may be missing a large fraction of the energy and where it's coming. And secondly, there's a related issue here where these are two plots taken from Erica's compilation where she took two different common light curve fitting tools. The one on the left is TDE mass, which is based on that self-intersection model. And the one on the right is MOSFET, which is based on the idea that there's an accretion disk that's accreting and being reprocessed. And you fit those light curves, they go up, they go down, you get a model, it goes up, it goes down, it goes through the data, looks great. It fits a black hole mass. And then if you plot the inferred black hole mass versus the mass of the galaxy, I hope you can agree, neither of those shows any correlation whatsoever. And one thing we know about supermassive black holes is that they should correlate with the properties of their host galaxies. So there's still very much a crisis for understanding the early time optical emission from TDEs. We don't understand what we're looking at, but we can model it. We can model it many different ways, and they're equivalently good. Yes, these are the same events being fit in different ways. And yeah, there is some correlation because they're picking up on the similar timescales in the light curves. Yeah. Yeah. And one other point I wanted to make about the previous work was you can use this to start talking about TDE rates. So this is from Yuhan Yao's paper, where she took 33 spectroscopically confirmed TDEs from the first 3 years of ZTF 1 and 2. So basically 1 a month for 3 years. And she estimated the black hole masses using the properties of the host galaxies and host galaxy scaling relationships, and used that to infer something about the black hole mass function over these intermediate masses from about 10 to the 5 to 10 to the 7. And she very robustly sees that the event rate drops dramatically if you expect the black hole mass to be above 10 to the 8, entirely consistent with the event rate suppression. But the number she comes up here is for massive-ish galaxies. The number works out to be about 3 times 10 to the minus 5 per galaxy per year. So this is very different for different types of galaxies, and there's a whole story about different galaxy types here, but keep that number in mind. 3 times 10 to the minus 5 per galaxy per year. So a fiducial for an optical transient survey is the core collapse supernova rate is 10 to the minus 2 per galaxy per year. So the TDE rate is 1/300th of the supernova rate. And so we expect 300 supernovae per TDE. So if I'm out there classifying optical transients randomly, we'd have to look at hundreds of events before we found a TDE. And so that's why optically selected TDEs were not found until large optical surveys about 15 years ago. And the largest unbiased sample of a magnitude limited survey is the ZTF Bright Transient Survey, which to date, the numbers have been updated. We're now at about 10,000 classified transients above 19th magnitude. TDEs are 0.5%. So if you want to do science that requires a sample of objects that say 100 TDEs, you cannot do it through brute force unless you're willing to classify 20,000 supernovae first, okay? And so the reason why we've been able to select them as all is that we have applied what we've learned about the first few events to select things. They're blue optical transients. They exhibit slow color change, like I showed in the first plot. They're associated with galactic nuclei that show no previous sign of AGN activity. And each one of those bullet points is a selection effect and an assumption. So, and what's shown on the right here is from the first couple of ZTF TDEs. This is a measure of the decay timescales versus the rise timescales. TDEs are kind of here between the supernova 1A and the AGN. Over here, the rate of color change, they're pretty flat, kind of like an AGN, but they have different timescales. So theoretically, if you have a full light curve, you can easily classify with reasonable confidence what's a TDE, what's an AGN, what's a supernova. And so the theme of my talk is, well, what happens as we start to relax these assumptions? And one of our motivations for doing so is that numerical simulations of hierarchical galaxy formation have shown that we don't expect all the massive black holes in the universe to be right at the centers of galaxies. So we look for supermassive black holes at the centers of galaxies. That's where we found them. But depending on your prescription for merger histories of galaxies, about dynamical friction timescales and so forth, a significant fraction of, say, million solar mass black holes are not found at the centers of galaxies. And if they're wandering around in the halo of some galaxy, if they're not actively accreting, how do you find them? And one answer is if they're accompanied by some sort of star cluster that can produce a TDE and you can search for them. And we know that dual supermassive black holes exist. People have been looking for many years for AGN. So on the right here, this is famous NGC 6240, kiloparsec separation AGN. On the left, this is NGC 7727, which was found dynamically. We have a nucleus and a second star cluster of significantly low luminosity. It's about 500 parsec separation, and there's dynamical evidence for black hole in both. So expect as galaxies merge, black holes come together. All right? And there's some hint in the TDE world. There are these two X-ray selected objects. They're selected as X-ray flares. The one on the left by XMM slew survey. So there's a soft X-ray flare that occurred in 2006 that decayed. And it's localized to that little dot in the outskirts of that galaxy. Just last year, the Einstein probe found similarly an X-ray selected flare that did have some optical emission localized to that little dot in the outskirts of that big galaxy. And if we analyze the properties of both of those X-ray flares, they are consistent with being from lower mass black holes, like say 10^4, with respect to what we see from normal TDEs. And since there are little dots in the outskirts of galaxy, it's consistent with it being some sort of tightly stripped dwarf galaxy. So with that as background, let's start talking about AT 2024 TVD, which we found about a year ago. So this was first detected by ZTF in, I guess, August of last year. Started rising. It's very bright. So lots of people started getting spectra. Initial spectra showed blue continuum broad H alpha. By October, another group, Harris et al., classified this as a TDE based on broad hydrogen and helium-2 in the spectrum, central location of host galaxy, long-lasting UV detection. These are all classic signatures of a TDE. But what we noticed was that, and what sort of caught our eye, was that we looked at the position of the host galaxy in the legacy survey, Sloan, Pan-STARRS, et cetera. It's here. And all of our best fit positions are over here, about 0.9 arc seconds away. So ZTF has 1 arc second pixels. You have to be really confident in that position to say that 0.9 arc seconds is real. And so these points were actually measured by Charlotte Ward, who many of you know, who's here, using the Scarlet 2 code for scene modeling of the galaxy plus point source to try and measure the centroid as best as we can. And she got the ZTF here is the median position right here. And we noticed that the Swift UVOT position was also 1 arc second away. That gave us confidence. Well, so then we went to Chandra, and Chandra was able to measure like 20 photons, and depending on your Bayesian odds ratio formulation, it's like 3.6 sigma away from the nucleus. And then we were able to go to Hubble. The source wasn't actually visible to Hubble for the first couple of months, so we had to wait for it to become visible. And we got an HST image. And here's this nice, beautiful, smooth, early type galaxy with a nice blue point source 0.9 arc seconds away from the center, entirely consistent with our ground-based astrometry. So 0.9 arc seconds, and the distance of the source is about 800 parsecs. Okay. And secondly, we were fortunate that the VLA was in its highest resolution A configuration. And so we were able to follow it up. And I'll return to this later, but we can see right here, we have 2 point sources that are easily spatially resolved. And this is important because this is our transient. And that's the galaxy nucleus. And the fact that there's a radio point source in the galaxy nucleus means there's a black hole in the center of that galaxy still. Yeah. Okay. So what's going on here? So we looked at this TDE. The optical spectra are a little hard to analyze because there's a ton of galaxy light. But if you subtract off the archival Sloan spectrum, you get a classic blue continuum with helium-2, nitrogen-3, other sorts of high ionization lines. We've got a UV spectrum from HST. And again, high ionization lines, carbon-4, carbon-3, no magnesium-2. This is proved to be common for the sort of 10-ish TDEs with UV spectra, is that they don't show the strong magnesium-2 line that we see in quasars all the time, but instead we see high ionization CNO lines. Okay? So it looks like a TDE. The optical properties, we come back here. We fit the black body, we get a luminosity few times 10 to the 43, black body radius 10 to the 15, black body temperature 20,000 Kelvin. It's exactly like the median TDE in the previous sample that I showed you earlier. There's nothing about this event that would catch your eye as a TDE except for its location. And so on the right here, what we have is, this is a measure of the peak luminosity versus a time scale, and here's versus galaxy mass. And it's right in the middle of the distribution of ZTF TDEs. Yeah, so we will, it's detecting the X-ray, so there's plenty of ionizing photons. But in general, no. So I don't think I've applied the SED to show. But usually there's enough ionizing photons about. Sometimes these Bowen lines, so nitrogen-3 here, are very strong. And so that may require more EUV photons than we are assuming by fitting a single temperature black body. Yeah, it's a little hard to say, I would say. But the other thing here is plotted the peak luminosity versus galaxy mass. Here it is over here. So the median object that looks like this is in a galaxy that's a factor of 10 or so smaller. And so given that we don't really understand what the masses of these black holes are based on the early time emission, all we can say is it looks like the median ZTF TDE, and the median ZTF TDE we think is a 10 to the 6 solar mass black hole. The host galaxy itself is pretty massive. You can kind of see it stretching out all the way here. It's an early type galaxy. There's a velocity dispersion about 200 kilometers a second. If you apply m sigma, or the standard scaling relationships for the black hole, you expect that galaxy to have about mass of a black hole of a few times 10 to the 8. So it looks like a million solar mass black hole, plus or minus 1 in the exponent, around a 10 to the 8 galaxy where you expect 10 to the 8. Okay? There's radio from the nucleus. The X-rays are from the transient, and we know that because there's a deep E Rosita pre-non-detection, or pre-observation non-detection, yeah. Yeah, and the X-rays are luminous. They rose to 10 to the 43 ergs per second, which is higher than a supernova by 2 orders of magnitude. Soft thermal disk spectra, like you would expect. And this is typical of TDEs. I'm not going to say too much about the X-rays, but one point I did want to make here is that we fit a simple disk model plus a simple power law for comptonization. We find that the fraction of upscattered photons is basically 0 until about 80 days after discovery, and then there starts being a non-zero upscattered fraction as presumably a corona builds and hot electrons are upscattering soft X-ray photons. So this all seems like a very well-studied but normal TDE. The radio, however, was completely a mess. So what's shown here are our two of our observations in the radio with the VLA, where again, we're in A config, so there's the beam. You can see it's a few tenths of an arc second, so amazingly convenient. So at 88 days, we happened to trigger an observation through Kate Alexander's large program, and we detected the host and not the object. We actually got our next observation about 20 or 30 days later. It's not this one, it was before that, but this shows it even better. Boom, there's suddenly a transient. There's still the host. It's still sitting there, perfectly happy. So compact non-thermal source at the nucleus is a standard low luminosity AGN. It requires a black hole to remain there. But this TDE had an amazingly sharp rise up to peak flux. So radio emission from TDEs is a whole different story. There are outflows in a very small fraction. We think something like 10 to the minus 4 of TDEs, they produce relativistic jets. But the majority of TDEs don't do that. And instead, 10 to the minus 4 is the observed rate. It's 10 to the minus 2 if you correct for beaming. So, but the majority of TDEs produce radio emission as there's some sort of outflow, and we infer velocities of 0.05 to 0.2 c for these outflows that are running over the circumnuclear medium in their galaxy. We don't really know what's launching them. There's various models involving accretion disk winds, collision-induced outflows, et cetera. But this went boom, way up, went down very quickly, boom, way back up again. And so if you fit this as a power law with respect to the time of discovery, you get absurd power law indices. And of course, that's a sign that the model doesn't work, and this isn't a turn on of something that happened at t0 equals discovery. But it probably means that the outflows were launched at late times. And so here's a couple models from, or some equipartition analysis from our postdoc Itai Sfaradi. And so by applying standard radiosynchrotron equipartition, the first radio flare shows kind of a linear rise with time, consistent with radius expanding at 0.2 c. The second outflow is even faster. And if you extrapolate these backwards, they must have been launched 80 or 170 days after disruption. So that's weird. What happened at 80 days after disruption? What happened at 170 days after disruption? Is there a natural timescale? The answer is no, but we've actually seen delayed outflows launched in a number of TDEs. So out here, this is some TDEs from the literature that have famous read-write names. So it's not completely unusual. So the possibilities are that it's some sort of prompt outflow that has a very peculiar density structure in the medium that surrounds it, or it's a delayed outflow. It's not launched until about 80 days after discovery. And that, coincidentally, is the time at which the X-ray corona starts appearing. If you've studied X-ray binaries, there's frequently a connection drawn between the production of an X-ray corona and mass ejection and radio emitting outflows. So it's at least plausible, which is good, but we don't really understand the radio emission here. We don't really understand the radio emission in general. So what caused this wandering black hole? There's kind of three, yes?
Stellar light is kind of unambiguously peaked at this thing you call the host.
Yes.
So there's really no ambiguity. Is there a possibility, for instance, that it's a double nucleus?
Yeah, so there's a paper by Kishore Patra using JWST data where they fit the location of the source right here. It's still bright and it's outshining everything, but they say there's marginal evidence for a nuclear star cluster surrounding it. Because to produce a TDE, you need not just a black hole, you need a star. You need a star kicked in. And so the ratio, however, is pretty large between whatever's at that versus here. It's at least a factor of 100 to 1, I think, in terms of the mass. No, they're not modeling image subtracted flux. What they're modeling is JWST IFU data, which show an upturn at long wavelengths. And so you can either model it as some sort of What? Yeah, so we have some good estimates of what the UV flux from this galaxy is. Yeah, so that's not controversial. On the infrared. Yeah. Okay. Right. So minor merger. So I just showed you that image. I didn't show you the smooth subtracted one. There's no sign of recent disturbance. So there's a companion galaxy off to the side, but there's no sign of a bar, dust lane, anything that it would indicate that this recently experienced some sort of merger. Could be ejected in a three-body interaction. If you have multiple black holes going to the center, there can be a three-body interaction that ejects the lowest mass one. And the problem with that is a bit of fine-tuning. 0.8 kiloparsecs is a strange distance, because if you have a multi-body interaction, the velocity dispersion of the bulge is something like 200 kilometers a second. You eject a black hole out at a few hundred kilometers a second. The most natural thing is that it goes out on a very eccentric orbit, and then it stalls and it comes back. And so it's spending most of its time at large apocenter distances, right? 0.8 kiloparsecs would have to be kind of fine-tuned, or we caught it right when it was passing through on its way out, which is also fine-tuned. And recoil from black hole merger is the one thing we can disfavor due to continued presence of at least one supermassive black hole in the center. Great, so we found one in a sample of order 100. That means this happens 1% of the time, plus or minus 1%. So those are some astronomer statistics. We're doing it. Yes. Yeah, so it's fading quickly, which is kind of the strange part. So this is the light curve as of the publication, but we have more data points. It's fading. At this point, though, even though it's fading quickly in terms of a power law fit, it's still years. And so with James Miller Jones in Australia is leading the VLBI effort. Yeah. Whoops. Okay, so moving on a little bit, another place where we don't expect to find black holes because of the cuts that we place on them are in dwarf galaxies. So a lot of people have become interested in what is the occupation fraction of intermediate mass black holes in dwarf galaxies. This is important for the growth of seeds at high redshift into supermassive black holes today. And depending on your models, numerical simulations show that a significant fraction of current day MBHs are off nuclear. They're either off nuclear in a more massive galaxy, or they're in a tiny dwarf galaxy. And in the tiny dwarf galaxy, the MBH may not remain right at the center the way it does in the big potential well of a massive galaxy. And so we miss these through traditional searches because they may not be at the center, and we may not see the galaxy to even associate with the galaxy. So Jean Samowar, who did this as his thesis at Caltech, is now a postdoc at Berkeley. She decided to do a systematic survey for things that look like TDEs but have no associated host galaxy, either large offset or really faint. And so she found this object called AT 2024 PUZ, which had no visible host galaxy in standard ground-based, pan-stars imaging, 22nd magnitude. With HST imaging, we can see a tiny little fuzzy compact dwarf host galaxy, and this is the transient all the way over here. So here's the light curve, goes up and down on a rapid time scale. You can see this is rest frame days, so this is decaying on a 10 to 20 day time scale. Luminosity is quite high. So if I put some numbers on here, numbers are here. Here's PUZ. UV optical component is above 10 to the 44 ergs per second. There's a highly variable X-ray source associated with this, also above 10 to the 44 ergs per second. If we look at a luminosity versus timescale plot, it falls in the middle between the luminous fast blue optical transients, which I'll talk about at lunch, and the classic TDEs. So what is this thing? The optical spectra are basically completely featureless, except for the interstellar absorption lines from magnesium-2, which give us the redshift. It's blue, it's hot, it's highly variable in the X-rays. It looks kind of like a TDE, also kind of looks like a fast blue optical transient. Some people propose that these are related, and this is an IMBH TDE, or this could be a stellar mass accretor. So we'll talk more about the LF bots at lunch, but likely a black hole is accreting, but I don't know if the mass is 10 or 10 to the 4 solar masses. It was not detected in the radio, and it's not as constrained as you would like because it's at redshift 0.36, which is farther than most of the ones we detect. So you can rule out some corner parameter space, but there's a lot there. Yeah, there's a significant power law. I don't have the plot. Yeah. Yeah, exactly. The two IMBHs at the beginning, it was a very thermal, very soft spectrum. Here, this is more power law, which is actually kind of like the fast blue optical transients. But since we don't really understand why those are power laws, you know. Yeah. So now I want to sort of transition to thinking about the future. And I have a couple points to make about the future and where we're headed with this. One, as everybody knows, LSST is starting soonish, and we'll get a bazillion alerts per night. And people simulated TDEs and said that you can find maybe 50,000 TDEs over the 10 years of the survey. So how do we use limited follow-up sources most effectively? One advantage that LSST will have that ZTF does not have is it has U-band. And the more you go to U for something that's 30,000 Kelvin, the more you're likely to detect it. But how often will it be observed? A second point that is more subtle is that with ZTF, we have 1 arcsecond pixels. So if you're looking for offset TDEs, this is a real obstacle. So we've worked with Scarlett to try and model a whole bunch of our TDEs, because if we formally fit the centroids of our TDEs, we find a couple at 1/4 arcsecond, 0.3 arcsecond. When we have high resolution imaging, none of them hold up as being actually off center. There's just a systematic astrometric floor when you have poorly sampled images to a fraction of a pixel. LSST will have a much finer pixel scale, which will be extremely useful for this sort of work. But more generally, we have to use machine learning classifiers to even figure out what to look at. And this is a typical confusion matrix for transients from Ashley Villar. But it's important to think about what machine learning can do. Machine learning is excellent at doing real bogus. So whenever we have an alert off the telescope, which is a lot per night, we can figure out what's real. It's very good at separating long-term variables and AGN from things that are transients. Transient classifiers are quite good with type 1a supernovae. And that's just for 2 main reasons. One is that they're homogeneous, and the other is base rates. 70% of random optical transients are type 1a supernovae. If you had a classifier that said type 1a supernova 100% of the time, you would be outperforming some of the classifiers that are on the market a few years ago. So classifiers are much, much worse with rarer classes of transients and on fast timescales, because you just don't have as much information. And so classifications become better as more data come in. That's good. But what if you need to make decisions to idea to something interesting to trigger follow-up? How do you find novel class objects? How do you find things like the TDEs I showed you at early times? And so within ZTF, we've been using Robert Stein, who's now a postdoc at Maryland, his TDE score, which is based on a machine learning algorithm that is used a whole bunch of potential parameters about nuclear transients in ZTF. And with full light curve information, TDEs can be identified relatively reliably. But if you look at what the most important features are, number 1, WISE W1 minus W2. This is looking for hot dust in AGN. And so if your survey is shallow, like ZTF, you can detect the hot dust from an AGN. If your survey is deep, like LSST, WISE will not detect them either way. There's peak color. There's rate of color change. All the most important parameters are things that you won't measure, after your first 3 data points come in. So, but moving to early times is where really the frontier is here. Most TDEs only have multi-wavelength data taken after peak due to the time it takes you to realize that's the interesting one and then to classify it and so forth. You can kind of see that here from this sort of compilation. This is optical light curves of family of TDEs compared to the UV light curves. You notice that here you have nice, beautiful rises that you pick up passively because you have a survey that is repeatedly imaging, whereas here you actually have to trigger observations, and so you don't get on them until after maximum light. But there's a lot of stuff going on. All that stuff at the beginning about the different physics about for why we're actually seeing light might have different signatures at early times if we could ever get multi-wavelength information at that time. And so this is sort of the third push that we've been making, is going to earlier and earlier times for infant TDEs. And so with TDE score, you can throw out the characteristics that you don't actually measure. And so these are the precision and recall curves as a function of threshold. Full TDE scores in the orange, and early is in the red. So to get significant recall at early times, you have much less precision. It's just inevitable. There isn't enough information. So in order to find early time TDEs, you have to throw a lot of resources at it. But if you can make the problem a 10-to-1 problem instead of a 300-to-1 problem, it starts becoming more feasible. And that's what we've been doing over the past 2 years, and what's enabled a number of these discoveries. Because in the last year, we've been finding TDEs about the rate of 3 times a month. That's up by a factor of 2 to 3 above the early days of ZTF. And it's the same telescope, same survey. It's just we're finding a lot of the fainter ones, as it turns out. And the fainter ones we're finding are not low luminosity ones, they're just the more distant ones. But with the larger sample of objects, then you can go realistically and search for the 1 in 100 objects like the one that's offset from the center of a galaxy. You can build up a sample that way. And so within ZTF, we have a public data stream. Lots of people are looking at it, not just us. And over the past couple years, basically everything that people have found in our data stream are things that either we classify, that's about half of them, or other people have classified that were on our sort of candidate list. There was one big exception for an object that we missed, and it happened last week. So this object, 2025 AARM, it's at 60 megaparsecs. It's one of the closest TDEs in the last decade, and we completely missed it for reasons that are unbelievably bad. Intersection of failures, basically. How can you even miss a 16th magnitude transient? But now in red and blue here, this is the light curve of the TDE. It's still rising. It's found around October 1st. Pre-peak, it was classified by another group on October 30th, so last week. And we immediately said, huh, how did we miss this? It turns out it's because it had a non-zero Gaia parallax for the host galaxy. That was a big component. There's a lot of galaxies in the sky. There's some outliers out there. And so now, for the first time, we have an existing HST UV spectroscopy program led by Erica Hammerstein, which will get data on Friday, I think. Starting tomorrow, we're going to get very deep Chandra and new star observations to constrain the X-rays before maximum light. This is the first time we've been able to go so deep, so early, and we could have even done it weeks earlier if we had actually looked at our own data. So one of the things we're hoping to see is signs of these disk formation processes before maximum light, before peak. So the UV optical component here, it's rising. It's something around 10 to the 43 ergs per second once you apply the bolometric correction. We're going to reach flux levels in Chandra of a few times 10 to the 39. So we should be able to detect any X-rays that are being produced by either shocks or accretion at the level of 10 to the minus 4 bolometric, which is a gigantic ratio. And that's happening tomorrow night. And so expect to hear a whole lot more about this very, very soon. And so at the very end here, I wanted to throw up a couple slides about ongoing projects that will help expand things in the future to advertise them. So one is that Berkeley is one of the founding members of something called the Lacia-Schmidt Southern Survey, LS4. So in the era of Rubin, there's still a lot of room for other things to be done. There's lots of areas of the sky that Rubin's going to get at low cadence. So we want something that's shallow and high cadence to fill in the things that Rubin can't do. And so the 1 meter Schmidt at ESO and Lacia was unused. And we refit the camera with GI and Z filters. And we'll focus on trying to do brighter, more nearby objects. And so the basic parameters are that we have GI and Z. And we will be doing 90% of our time on a public survey with relatively high cadence. And typically, what the cadence means is you get G and I one night. The next visit, you get I and Z. So you always get a color. And the idea is we're going to 21st magnitude, similar to ZTF, but over 20 square degrees. And so we'll be able to do a significant fraction of the southern sky at high cadence to complement Rubin. And so when Rubin is doing its survey, there's large areas of wide field deep that are not getting the rolling cadence and will have slower cadence. So we'll fill in the bright objects, which will help immensely. And so here we are on the plot of field of view versus primary mirror collecting area. We're kind of half a ZTF, but much better than some of the predecessor surveys. And the other thing that I want to advertise is put on my other hat, which is I'm a science team member for UVEX, which is a NASA mid-X mission that is going to be launched in 2030, we all hope. And this is an ultraviolet focused mission. It's Ultraviolet Explorer. It will have 3 instruments, a near UV imager, a far UV imager, and a UV spectrograph. And time domain capabilities are built in from the beginning. That 3-hour TOO response time. We can do multiple cadences. And so here's kind of the optical design. We have a near UV and far UV passband, as well as broadband spectroscopy across the far to near UV. And this will be transformative. And one of the reasons it will be is you have the fast response time compared to Hubble. So with Hubble, the very fastest response you can get is 48 hours, not 3 days. And so that's great for gravitational wave follow-up. Hubble has a very limited number of TOOs that have faster than 15-day turnaround, whereas we're going to regularly do 3 hours or 6 hours, depending on. The other thing is, if you've never looked into it before, the UV spectrographs on Hubble have extremely low throughput, talking 1% to 2%. We're going to be in the regime of 15 to 20%. So that's why with a smaller telescope, you can actually have Hubble quality data. 0.76. Yeah. Yeah, so Ultrasat, the timeline's a little fuzzy to me. I think it got delayed a little bit. It is a single band near UV imager that will be launched in 2027, I think. And so, yeah. Look, we're saying 2030 as well. You know, we all understand there's potential delays in space missions. And so Ultrasat is an Israeli mission. There's some US participation. It's a near UV imaging only. They have a region of the sky near the celestial poles that's going to be repeatedly imaged on a fast cadence. And then they have slow cadence build up the rest of the sky. And so it's designed to look for things like supernova shock breakouts. But it will also be useful for things like TDEs in the same way that UVEX will be. The big difference is that they have 1 filter, not 2. So you can't do UV color, and they don't have a spectrograph. So it will be great for getting light curves of fast evolving things. I think they'll do just great on finding shock breakouts and such. Yeah, and just wanted to point out a few things, may be obvious, but UV is very important when you have objects that are 30,000 Kelvin. They're bolometric outputs coming out in the UV. We're wagging the tiger by the tail here. This is a plot of the Sloan composite quasar spectrum. This is the optical portion of the spectrum. This is near UV. This is far UV. Atomic physics dictates that the typical resonance lines of these ions have energies around 10 electron volts. They're in the far UV. Think about all that we have learned from quasars. Now imagine you had to limit yourself to everything you could only learn from the optical portion of the spectrum. No high redshift quasars, no rest ring UV. Imagine how impoverished our understanding of quasars would be. Well, we're in the same boat with TDEs and early supernovae, because we're looking at this part. We're not, everything, including and specifically relevance for TDEs is that in quasars, broad absorption lines are commonly seen in the UV resonance ions like carbon-4 and such. And those are things that are inaccessible from the ground. But it's something that in a TDE, there's some evidence for broad outflows in these objects that are only seen in the UV spectra. And we simply cannot see them in the optical. So to wrap up here, I say TDEs exhibit a range of accretion phenomena in the same event as mass fallback rate changes by orders of magnitude. They are wonderful laboratories for studying the physics. We've demonstrated that we don't actually understand the physics, so that means that there's lots of exciting work to be done. But even assuming that we don't understand the physics, we can still use the existence of these objects as probes of the presence of black holes. And I gave you kind of 3 examples of ways in which we're pushing by trying to up the discovery rate. And they find rare events. One, we found one offset TDE. Hopefully we can find another without waiting for another 100 to be classified. But these are new probes of the wandering supermassive black hole population that theoretically, at least, we should be able to find other wandering supermassive black holes in the outskirts of galaxies and learn about their presence, that these black holes you will otherwise never detect. TDEs are also going to be an important probe of MBHs and dwarf galaxies for multiple reasons, and we're trying to push on that very hard. They've been overlooked in a number of surveys due to a number of selection effects. And if you have a bright transient that says, hello, there's something here, pay attention. And the other way which we're pushing is this early time discovery. It takes a lot of false positives of type 1a supernovae, but if you can find objects at early times, you enable studies of physics that might help answer, or at least rule out, some of the popular models for the emission processes. And the future relies on progress in the machine learning algorithms to help us figure out what the best ways to use our telescope time are. It's a limited amount of information out there, and we have to use it wisely. Thank you.
Sure.
Yeah, so as you mentioned briefly, the very early theoretical models of these events, before any were observed, predicted that most of the emission would come out as kind of electron radiance from extreme UV or very soft X-rays. And I recall one model particularly familiar with it. It was about a 7 magnitude volumetric correction in the optical. So can you rule out the existence of, you had this luminosity problem.
Yeah.
Is there such a component based on what you know about lines and things?
So people have made some arguments based on things like helium-2 assuming, and nitrogen-3 assuming that these are powered by recombination. What ionizing flux do you need to power the observed line fluxes? And this gives us some information, because I don't have the plot, but you have some UV optical component like this, you have some X-ray component like this. You want to draw a line across there because you can't see it. But these high ionization lines are sensitive to the ionizing flux in between. And so they give you some constraint, some. I don't think you can hide the orders of magnitude of light, but we're probably underestimating things with single temperature blackbody fits. Yeah. Yeah, I think it's an interesting question, actually.
If you remove the constraint that you're not looking at sources that had known quasars in the nuclei, AT and the nuclei, how many events do you see that look like your TDEs?
It's a very tricky question. Yeah, because we don't even, just given the interests of the people, we don't invest as much time in things that look like changing look AGN. We see them. There's a number of cases of things that look like TDEs that are kind of ambiguous. And so I think what Robert's getting at here is that we throw away things that either have red Weiss colors, or have the existence of the hot dust, which indicates an obscured AGN that has a torus that's absorbing and re-emitting. But we also throw out things where there's a history of optical variability. But there's things with optical variability that's within a certain range and it goes boom. Like that could be a TDE and an AGN. But they get mostly filtered out, except in extreme cases where they become so obvious we can't ignore them. And so we have not been interested enough, or the individuals involved have not been interested enough to try and quantify that. But we definitely have objects like that. Yeah, so you're thinking of something like a changing look AGN or something.
I don't believe in TDEs yet. They may all be changing look AGN.
So they may all be changing AGN. Yeah. So I think in some cases we can rule out the presence of dust of a torus. So depending on what you believe for your changing look AGN, how much of a disk had to be there beforehand, I think that would be the strongest argument.
I was under strict instructions not to go past 12, so it's lunch, but we'll continue these questions there. Thank you very much.